Okay, so hello everyone. I would like to first start by thanking the organizers of this public series of talks on infrared astronomy. And today I'm going to be talking about unlocking the chemical composition of the galactic center of the infrared spectrum. I know that maybe this is a technical title for many of you. I'm not going to assume any previous background, so I'm going to go into the details of each one of these components that I mentioned in the title. So the three components that we have in the title are the chemical composition, details about our galaxy, and infrared spectrum. We're going to start with the chemical composition because maybe that's the part that most people are familiar with. So whenever we talk about the chemical composition, we think about the periodic table with all the chemical elements that it has and all its details. So the first question that maybe comes to mind is, why do we talk about the chemical composition in an astronomy talk? These are talks about astronomy, infrared astronomy. So what does this have to do with the chemical composition? To answer this question, maybe we should think of a much bigger question, or a much deeper question, and ask, what do we know about the chemical composition of the universe? Then when we talk about the universe, it's clear now that we're talking about astronomy. So we know that the universe started with a Big Bang. And when we study the first generation of stars that formed right after the Big Bang, we see that the chemical composition is roughly 75% hydrogen, 25% helium, and a very, very small fraction, almost negligible, of the very light elements in the periodic table. However, the current composition of galaxies is much different than that. We have about 75% hydrogen, but only about 23% helium, and then a higher percentage of all the remaining elements, which is about 2%. So of course, the 2% is not a very big percentage, but when we compare to the initial composition of the elements that were there and the first generation of stars, we see that is a significant change. So here, I want you to see these two things that changed. One is the amount of these, all the remaining elements other than hydrogen and helium, but also that now we have much more elements that were not there in the first generation of stars. So then the question becomes, what caused this change in the chemical composition? It's not the same, so that there is something that is changing this composition. And where did the new elements come from? And when I talk about the new elements, I talk about the other elements in the periodic table that we're familiar with, like calcium, magnesium, iron, and so on. The answer to this question is stars. So elements, the different chemical elements, or most of them, are formed in the core of the stars. And to just give you a brief background about this, different stars would have different life cycles or lifetimes depending on their initial mass. So we always, whenever we talk about stars, we like to start talking about our own sun because that's the star that we know the most. And currently the sun is in a phase where in the core of the sun, the hydrogen is fused into helium. So there are nuclear reactions that are taking place in the core of the sun. And as long as these nuclear reactions are happening, the sun will be the way we know it today. But eventually, the sun is going to run out of the hydrogen in the core. So what is going to happen then is that the inner core is going to shrink. So basically what keeps the sun in its current position or current shape is that there are two forces that are balancing each other. We have the pressure inward, the gravity inwards and pressure outwards. However, when these nuclear reactions stop, or they're not as they are happening now, the outer layers will expand due to the pressure, and the inner core is going to shrink due to gravity. And during that phase that we call the red giant, that's not the end of the life of the sun. It's just an intermediate phase, because as the core shrinks, it keeps shrinking until the pressure increases, and as a result, the temperature increases. So now the core that is made out of helium is going to reach the temperature needed to start fusing helium. So the same story happens again. Helium is being fused into carbon and traces of oxygen, and that's going to continue until the core runs out of helium. So the idea that I want you to get out of this is that As the stars age, they are producing different elements which were not there in the initial composition of the star. And then the interesting part is that with time, so after, for example, a low mass star like our sun runs out of helium, now the main core or the core of the star is made of mainly carbon and traces of oxygen. The star will again have its core shrinking, but because it's a low mass star, it will never reach the temperature needed to start fusing carbon into heavier elements. So that's going to basically be the end of the life of that star. The inner core is going to be called the white dwarf, and that's what you see here in the middle. The outer layers are going to be expanding peacefully in the interstellar medium. So here there's no explosion, nothing fancy. That's going to be the end of the life of a star that has a low mass like our own sun. The story is a bit different if we're talking about a heavier star. So it has an initial mass much greater than the initial mass of a star like our sun. Because those stars are having more mass, those are going to continue. So after the core of the star reaches the phase of carbon, carbon is going to reach the core is going to reach the temperature needed to fuse carbon, and the nuclear reactions will keep going until, as you can see here, is an example of sequence of the elements that are being formed, until eventually iron is going to be in the core of that star. But then, because of the so iron is the most stable element, so then the star will not be able to sustain itself anymore. It cannot keep going with these nuclear reactions. So then the star is going to eventually explode. And that's what we know as the supernova. Now, the outcome of the supernova is either a neutron star or a black hole. And I know that these are fancy components and fancy topics that people like to hear about. But here we're not going to talk about that. We're going to basically talk about the supernova, because this is the explosion that's going to eject all these new elements that formed in the core of the star into the interstellar medium. So if we want to summarize all this, we now know that based on the initial mass of the stars will have different life stories. The low mass stars like our sun, here, is going to end up as a white dwarf, and the material is going to be ejected as a planetary nebula. However, the higher mass stars will end up in supernovae. And these different ending of the life of stars are going to enrich the interstellar medium with different elements. So this is the important part that we want to get to, which is that if we compare the interstellar medium, and that's the medium that's between stars, that we started with when all these stars initially formed, and we compare it with the interstellar medium that is going to be after all these stars live their life, we see that the chemical composition of the new interstellar medium is going to be much more enriched, which means that we will have much more chemical elements compared to the initial interstellar medium where all these stars started with. So now that we understand this, we can think about the periodic table from astronomers' point of view, because if you followed what I mentioned, you would see that the most important elements that we care about in astronomy, roughly speaking, are hydrogen and helium, because those are the most abundant elements in the universe. Everything else in astronomy is called a metal. I know that this is strange, but this is how we call it. And another interesting element here is iron, because iron is the end where after having iron in the core, the star is going to explode. Now, some technical words, we don't have to go into the details of this, but just some technical information about how we refer to the chemical composition in astronomy. So the most abundant elements are hydrogen and helium. Everything else, as I said, is called a metal, and that's why when we want to refer to the chemical composition in astronomy, we just use the word metallicity. So metallicity is basically the mass fraction of all elements other than hydrogen and helium. Okay, so that was about the chemical composition. Now let's talk a little bit about our own galaxy, which is, as we know, it's called the Milky Way Galaxy. And let's try to put it in terms of scale. So we know that we are humans living on this nice planet Earth, and our planet is part of our solar system. And in the solar system, we have one star, which is the sun, and that is, so this is the location 2/3 from the center of the galaxy. So we're not in the center of our galaxy. And then our galaxy is one of the many galaxies in the universe. And by the way, just a side note that this picture here, whenever we see a picture like this is not really the picture of the Milky Way, because we're not able to take a picture of the Milky Way like this because we live in the Milky Way. Nobody was able to get out of the Milky Way and be able to take a picture like this. So usually we use pictures of similar galaxies to represent our own galaxy, but we do not have a picture like this for our galaxy. The picture that we can see for our galaxy is a picture like this. And many of you maybe saw this in the night sky, especially those of you who are lucky to live away from the light pollution and so on. So this is the shape, or this is how we can see our galaxy, or basically the central region of our galaxy in the night sky. And our galaxy is made of stars, but also, so some of these stars are formed into star clusters. So they're a group of stars, which I'm going to talk about in a moment. But also there is dust and gas that is not in the form of stars. So just to get an idea of how the galaxy looks like, because when we see the galaxy like this, we cannot really tell how it looks like. But this is a sketch of how our galaxy looks like and the different components of our galaxy. So we have some main parts for the galaxy. We have the galactic center, which is obviously in the center. And then we have the galactic bulge around it. We have the galactic disk. And then finally, we have the galactic halo around it. And as you can see, as I mentioned earlier, the sun is about 2/3 away from the center of the galaxy. And sorry, so one more thing is that here you have some details about the distances, because as you can see, the distances are huge. And that's why I'm going to talk about some challenges that we face when we try to study stars or star clusters near the center of our galaxy. So the distance, roughly speaking, the distance between the sun, which is our star, and the galactic center is about 8 kiloparsec, which is about 26 million light years. And of course, that's a very large distance. Okay, so as I said before, some of the stars in our Milky Way are not formed as individual stars, but rather as groups of stars, which are gravitationally bound together. And those star clusters, in addition to being very bright, very bright and very beautiful, they are very useful in trying to understand the chemical enrichment or the chemical history of different galaxies. Yeah, so sorry, I just saw the questions, so I'm going to answer the questions in maybe at the end of the talk, so that's better. Okay, so yeah, so the star clusters will help us trace the chemical history of different galaxies. And the important thing to know about these star clusters is because they are forming from the same interstellar medium or interstellar cloud, they are born around the same time, so they have the same age. All the stars in the cluster have roughly the same age. And they have the same chemical composition, because that's the composition of the cloud or the interstellar medium that they formed from. Okay, so an interesting thing that I would like to discuss is that there are some recent discoveries of some clusters, very young, massive clusters near the center of our galaxy. And the interesting thing about these star clusters is that they have dozens of red supergiants. So I'm going to talk about the supergiants in a minute, but you can see here in this figure that this is the central region of the Milky Way. And those are the locations of the star clusters that have red supergiants in them that have been discovered in the past 15 years or so. And this is an image of one of the possible star clusters. And these dots are the actual stars, the red supergiant stars, which we are going to be talking about. And the nice thing about these star clusters is that they're ideal to study the most recent and violent star formation events in the inner galaxy. And you're going to see why I'm calling them the most recent star formation events. It has to do with the fact that the red supergiants are young, which means that if we see or if we observe a star cluster that has red supergiants, it means that this is a young star cluster, which means that it formed recently. And of course, when I say recently, I mean recently in terms of astronomy, so in the time scale of astronomy. So what are the red supergiants? First of all, they are evolved stars, which means that if you remember when I mentioned the different stages that stars go through, the first stage is fusing hydrogen into helium. So the red supergiants finished that phase. So that's why we call them evolved stars. They have masses between 10 to 30 solar masses, which means that they're about 10 to 30 times much more massive than our own sun. They are among the largest stars in the universe in terms of size, and they are young. And that's why this is the important point. That's why when we observe star clusters of red supergiants, we know that those are young clusters, which means that they formed recently. And then, so they have certain spectral classes like K and M, which means that they are cool and red and luminous. And the point that they are luminous is going to be very important for us because that's how we can actually see them and we can observe them. And one famous example of red supergiant is Betelgeuse, which is in Orion constellation. Maybe many of you are familiar with it. Okay, now, as I said earlier, so in addition to the stars and the star clusters that we have in a galaxy, there is also dust and gas. And the problem is that because these clusters that we're trying to study, like the red supergiant clusters that I mentioned earlier, because they are very far away from us, as you saw, the distance between our sun and the center of the galaxy is a very large distance. And because of that dust between us and the center of the galaxy, these clusters can only be studied by looking at the actual red supergiants inside these clusters. And then another challenge, another challenge is that because we have the dust between us and the star clusters that we're trying to observe or we're trying to study, dust causes scattering of light. So when the light of a star is trying to pass through that region that is dusty, it's going to be scattered. So in the end, we will not be able to get the entire picture that we want to get. But the good thing is, and this is why infrared astronomy is important, is that the infrared spectrum gets less affected by the scattering than the optical light. And that's why the studies of these red supergiant clusters that I'm going to discuss focus on the infrared astronomy. Which brings us to the third component, which is what are the infrared spectra, or what is infrared astronomy? To answer this, we can think about the spectrum that we get from the sun, for example. It goes from a very long wavelength to very short wavelength. The longest wavelength starts with radio waves, and then microwaves, infrared, which is what we're going to talk about, and then optical light, which we're familiar with, ultraviolet, X-ray, and gamma rays. So the idea here is that based on the wavelength of the region that we're studying, it will be affected differently by the scattering. And the good thing is that infrared light gets less affected by scattering than the optical light. Okay, now I mentioned all the challenges that we're facing. I mentioned that the center of the galaxy is far away from us and it's covered by dust, so light is going to be scattered and so on. But the good news is that we now have the tools to be able to explore that region of our galaxy, and different research groups tried to study that part of the galaxy, and now we have some information about it. And that's in order to understand or in order to study this, we need two things. One are the advanced telescopes. So we need very large telescopes to be able to observe these objects that are very far away from us. But also we need the computational facilities that allow us to create theoretical models for us to compare with these observations that we're observing. And luckily we have both of these. But then the question becomes, what is the importance? So we're trying to learn about the chemical composition of the different star clusters and their ages. But what's the point? Why do we need to know this? And the answer is simple. If we want to know the chemical history of a galaxy or a group of star clusters, we need to know their chemical composition and their age. So age, which is time, tells us at what time in the history of this galaxy this chemical composition happened or was there in the galaxy. So if you want to think about it, you can think about the history of different cities can be learned through the ages of the population of that city. So we have people of different ages, and that can help us trace the history of that city. The same way is done using star clusters. So we observe star clusters of different ages. Some of them are young, some of them are old. And then we can get the metallicity or the chemical composition of these different clusters, and then have an idea about how the chemical composition changed over time for these galaxies. But an important point to mention here, as I said earlier, when we talk about people and the ages of people, if, for example, somebody has like 90 years old, we say that this person is old. Of course, in astronomy, the scale is much different. So just to get an idea, the age of the universe is roughly 13.8 billion years. The age of Earth and the solar system, because if you remember, we mentioned about the solar system as a whole. So the solar system is about 4.5 billion years. Here we're talking about billion years. But there are stars that are much younger than that, in the order of millions of years, like the red supergiant clusters. And that's why we call them recent events or recent star formation events, because they're much, much younger than the history of the universe and also our own solar system. And then, of course, there are stars that are older than our own solar system, and some of them are as old as the universe. Okay, so let's get to some results, what other people are doing. Different groups, different research groups are trying to use infrared astronomy to obtain the chemical composition or the detailed abundances of the different elements in the red supergiant clusters. So this is one example of some results. And some other groups are trying to map the Milky Way Galaxy and try to find the distribution of metallicity along the Milky Way Galaxy. So as you can see here, this is a map of the Milky Way Galaxy. And on the right, you see the scale of how the metallicity, which is the chemical composition, changes as a function of the location. And I'm going to end, so I'm going to talk a little bit about one of the projects that our group worked on related to this topic. So we studied the details of a star cluster, which is called the VDBH222. This is one of the red supergiant clusters, so it has many red supergiants in it. And this is a collaboration done with many astronomers from different institutes around the world. So the idea was that we use the VLT telescope, which is located in Chile. So this is an ESO telescope. We obtained the infrared spectra. As I mentioned, the reason we had to do the infrared spectra is because to avoid the scattering that's happening for the optical light. And we observed 6 red supergiants for that star cluster that we are studying. And what we were able to obtain is the different stellar parameters for these 6 red supergiants that we observed. As you can see here, these are the spectra of these red supergiants when they are compared to the models, and we were able to obtain parameters like the temperature and the metallicity and other parameters. And these parameters are important for obtaining the age and the chemical composition, which, as I mentioned before, is the main ingredient or the main quantities that we need in order to be able to trace the chemical history of that particular region of the Milky Way. So in summary, the chemical composition of a galaxy is enriched with time. So whatever composition we have now or we had at the time of the Big Bang is not going to remain the same. It changes, and that is due to the nuclear reactions that are happening in the core of the stars. So at the end of the life of the stars, all these new elements are going to be ejected, and the new stars will form from the new elements that are produced from the previous stars. Star clusters allow us to study the chemical history of galaxies. So those are important tools. In addition to being very nice objects, they are allowing us to study the chemical history of galaxies. And because of the large distance and the dust between us and the central region of the Milky Way, if we want to study star clusters, we need to study them by means of red supergiants, because those are the bright stars that we can observe from here. And then because of the scattering that's happening due to the dust between us and the center of the galaxy, we need to rely on infrared spectroscopy to be able to obtain information about these star clusters. So that's it. So I think I'm going to look now at the different questions and try to answer them. Yeah, so the question says, what do we know about our sun from observations of other stars or directly looking at our sun to understand the elements it contains, and different methods used to observe our own stars and other suns? Yeah, so this is a very good and interesting question. So basically, the sun is one of the most studied stars, and that's for obvious reasons, is the closest star to us. And that's why, in fact, if you saw that slide that talks about the way we refer to metallicity, which is the chemical composition, we always compare it to the metallicity of the sun, because that's the one that we know the most. So we can do observations of the sun, we can obtain the spectrum of the sun, and from the spectrum of the sun, we can find the elements that are there in the sun. So this is much easier than trying to study stars that are far away, like the ones that I mentioned, for which we have to overcome the dust that's between us and the center of the galaxy. So yeah, this is a good question. The second question, do galaxies that formed later or earlier start with a different enrichment of elements? Sorry, so I'm going to read it loud in case others do not see it. So do galaxies that formed later or earlier start with different enrichments of elements? Does this need to be considered when thinking about how much the star cluster have enriched the galaxy? Yes, so the answer is yes for both of these questions. As I said, because so stars form from the interstellar medium, and the interstellar medium has the chemical composition that is produced from the previous generations of stars. So as stars die, when they explode, for example, through supernovae, or at the end of their life, because there are different types of ending the life of the star, the chemical composition will change. So now when the new stars form and the new clusters form, they will have a different chemical composition than the other star clusters which formed earlier in the history of the universe. And this has to be considered when we study these star clusters, yes. So any other questions? Okay, so it seems that there are no any more questions. Thank you, everyone, for watching this, and I hope it was useful. Okay, so there's a question. Does merging of galaxies play a vital role in the chemical enrichment? Yes. So the answer for that is yes. And this is two parts. So first, when we observe a galaxy and we study the chemical enrichment of that galaxy, we can get information of whether there was a point in time where two galaxies merged together. So the chemical composition will change, because if the chemical composition is constant or it's going in the same manner, that means that it's just coming from the galaxy and its own clusters. But if all of a sudden that chemical composition changed, it could mean that that's because two galaxies collided or they merged together and so on. And that's a very important point, and this is one of the uses or the importances of studying the chemical enrichment history. Any other questions? Okay, so if there are no more questions, again, thank you everyone for watching, and hopefully this was useful.